Okay, so if you trudged through the calculus in the last slide, or if you just skipped past it, which is probably sensible, you will have discovered our integrated rate equation. And our integrated rate equation is an equation that basically says, hey, I'll tell you the concentration if you tell me the time and the rate constant. And for a first order reaction, it looks something like this. The natural logarithm of the concentration of our reactant A at time t divided by its value at the start of the experiment is equal to minus k times by the time. So there's really three things here, right, that can vary. The initial concentration A, the concentration at time t, and the time t. And of course, k is our rate constant. And if we know k, it basically tells us how everything's linked together. If we wanted to, we can actually get rid of the logarithms. Sometimes this form is more useful. So we can anti-log each side, and anti-logging a log just gives us whatever we were logging off in the first place. And if you remember, the anti-log of the natural logarithm is e to the power. And so we can go ahead and we can rearrange this expression and show that the ratio of A at times t over the original concentration of A is e to the minus kt. And so if we go ahead now and we just sort of cross multiply out the A sub 0, then we can see the concentration of A at time t is equal to the original concentration times by an exponential function. And the math department, they love this, right? Because they talk about exponential functions in their courses, and they try and convince you you'll see them over and over outside. And it's true, actually, you really will. And we can go ahead and we can plot this. And so this is A sub 0 and 0, and this is time down here. And if we plot an exponential decay, it's going to look something like this. It's going to start out, and as time goes by, it's going to go down and down and down. And if you can do a little bit of math in your head, you can see that since it's minus k here, the bigger k is, the faster it's going to drop. And so we could actually go ahead and we could plot this, and for large values of k, it's going to drop dramatically. And if you've got small values of k, it's not going to drop off so quickly. In fact, if k was 0, which it couldn't be, but if you could somehow imagine k approaching 0, e to the minus 0 times anything is e to the 0. E to the 0 is 1. That means that if you multiply something by 1, it's not changing at all. Okay, so let's look at an example of a problem that's a first order decay, and let's go ahead and solve for one of the four unknowns. So it turns out radioactive decay, it's not a chemical reaction, it's a nuclear reaction. But one of the cool things about nuclear reactions is that they're all first order. So that is, the kinetics is what we've seen so far for a first order chemical reaction. Now here's a neat one. So this is carbon 14. Carbon 14 is an isotope of carbon. It's got 6 protons and 8 neutrons. So one of the most amazing things about this, and this is an example of beta decay actually, is that one of those neutrons in the nucleus, carbon 14 has got 6 protons and 8 neutrons, but one of those neutrons that has no charge whatsoever can actually break down. And when it breaks down into a proton that stays in the nucleus, and it also forms an electron that's ejected out of the nucleus. In fact, you get a ray of electrons coming out of these atoms, hence radiation. Radiation is anything that moves in a straight line. So, of course, if you turn a neutron into a proton, your atomic number goes up from 6 to 7. That turns it from carbon to nitrogen. And the mass number doesn't change because you've just swapped a neutron and a proton around, and the mass number is just the sum of those two. Pretty amazing. So this process is very slow, and so if you look at the rate constant, it's times 10 to the minus 12, so that's 1/millionth of a millionth. Okay, incredibly slow. So here's a problem, and actually on the right, I don't know if you recognize this, this is an enhanced version are a processed version of the Shroud of Turin, which has been shown via carbon dating that the carbon atoms in there are nowhere close to 2,000 years old. And so this is thought to be a replica, a sort of a creation that, these cathedrals, they all had little bits of Jesus Christ or whoever that they would show, and it was just kind of a draw to the cathedral, let's say. But anyway, this has been dated using this process. Let's say we were given the value of K, and one cool thing is K doesn't change with temperature in these reactions. And we're given the initial concentration of carbon-14 here, and at some later date, the concentration is 3.84 times 10 to the minus 11. What's the time? So the initial concentration, it turns out that carbon-14 is a very teeny tiny proportion of all carbon atoms, and everything living takes in carbon, and so after a while, your concentration of carbon-14 is a constant value for all organisms. When you die, one of the things about dying is you don't tend to eat anymore, you don't take in carbon, and so the carbon-14 atoms that have snuck in there with the carbon-12 and 13, they get to decay away, and at some time, the concentration's gone down, and the question is, how long did that take? There's a few ways to do this problem. I think probably the easiest way is just to take the first order equation, so the natural logarithm of the concentration at time t over the original concentration is minus k times t. And what are we trying to solve for? We're trying to solve for t. So that means that we can go ahead and we can divide both sides by t. Oh, I'm sorry, we can divide both sides by minus k, and that will give us t. So t is the natural log of the original reactant concentration over, the final reactant concentration over the initial, all divided by minus the rate constant. And a lot of this we were given in the problem. And so we can just go back and look up those numbers. So it's the natural logarithm of the final concentration of carbon-14, and that is 3.84 times 10 to the minus 11 moles per liter. Tiny, tiny concentrations, huh? We divide that by the original concentration, so living organisms have a concentration that's about 5.83 times 10 to the minus 11 moles per liter. We can see the units are going to cancel, and that's good. Typically with logarithms, we can't take logs of things with units, and we're going to divide that by minus k, and k was 3.83, I believe, times 10 to the minus 12 per second. All right, so let's shift that up there. We can go ahead and we can calculate those values. We can break it down, so it's the log of 0.65866 with some guard digits over minus 3.83 times 10 to the minus 12 per second. And you might want to convince yourself on a calculator that this works. And you get, as the final answer, 1.09 times 10 to the 11. So it turns out the log of anything smaller than 1 is negative, so the top and bottom are both negative, giving us a positive value. That's good, because we probably want a positive time. And what are our units? Well, the bottom is reciprocal seconds, so if we take 1 over seconds, so 1 over seconds, you remember if you divide by a fraction, that's like multiplying by the fraction upside down, so it's 1 times by seconds over 1, and that gives us units of seconds here. And so about 1 times 10 to the 11 seconds. Now, if you do the math here, this comes out to be about 3,000 years. I think it's 3455 years. So, wow, that's a pretty long time, huh?